with the in-class assignment in it. This lecture is going to be the start of subgroups. And what I found the last time I taught the class is if you have a really good understanding of the subgroups, everything else starts to fall in place afterwards. So I'm going to be a little bit slower on these subgroups, going through it very carefully, and then use that as a jumping board for the rest of the semester. So I'm only assigning 2 homework problems, 51 and 52 on page 58. And actually, if you look deeply, I'm covering them in this lecture right here. So what is a subgroup? We are, by the way, on section 5, subgroups in the book. If I have a subset in a group, it's not necessarily a subgroup. Something is a subgroup if, in addition to just being a subset, if I use the binary operation from the big group itself, it itself by itself is a mini group inside the big group. So that's a formal definition of subgroup. So for example, if I have a group G and I have just the identity by itself forms a subgroup because the identity is in there. That's the first property of being a group. It contains an identity. Every element in H has an inverse element. Well, that's true because the only element is E, and E is its own inverse, so that's true. And is it associative? Well, yes, because there's only E in there. E star E is E star E, which is E, and vice versa. So it's pretty trivial. So this is called the trivial subgroup. Because it's really nothing, so it's always in there. So let's go to more interesting examples. If I take the integers, all the integers, and equip it with the binary operation of adding, we already know that that's a group. In fact, that's a group that I've avoided kind of playing around with too often with you because it's I'm having Ray call in so he can listen. So sorry for the break. But if I take the even integers, and that's a subset of Z, does that form a subgroup? Well, I have to actually start with closure because one of the first ways to get out of being a subgroup is that I can jump out of the group when I apply the binary operation. So is it closed? Yes, it is, because if I take an even number and I add an even number, my result is even. So it's closed under plus. That's the subset is closed under plus. Step 2, does it contain the identity? Well, the big set, the identity was 0, and the evens contains 0, so we're fine. It contains the identity. Does it contain all inverse elements? Well, that means that I should be able to get back to 0. and the negative of any even number is also even, and those are the inverses under Z. So therefore, the evens all have inverses contained inside their set. And last, is it associative? Well, yeah, because the original set was associative, so there's really nothing to show there. So that's fine too. So I'm done. The even numbers as a subgroup set is a subgroup of the integers under plus. Now, in undergraduate abstract courses, you go a lot over these modular groups, that modulo addition by modulo 2 or 3. And so I just want to give you a refresher of what we mean by Z sub n. So recall what Z is. Z is the number line that you've been playing with since you were in, I don't think they give you the full number line unless you're my son. He got the full number line. We had actually a huge number line on the floor with positive and negatives, and he'd walk around on it. So you get the full number line, I think, by 4th grade or 5th grade. So this is the number line. What is Z2? Well, Z2 is a packaging of Z into 2 boxes. So you can think of this as packaging up your kitchen and your house into boxes. And in one box, you have all your kitchen stuff. And in the other box, which wouldn't happen in our house because we have so much junk, but in the other house, in the other box, we put all the living room stuff. But I want to remember what's in the boxes because they're closed up. So here's Ray. Hi, Ray. How are you?
Hey, Professor. How you doing?
Good. Sorry about you not hearing. So that now I think everybody can hear.
Great, thank you.
We're talking about the packaging of Z into boxes. So in the other box, I have all the living room stuff, but I don't remember what's in the boxes. So I put a picture of one representative from the living room on the outside of the box, and that's the living room stuff, and one representative from the kitchen, a picture of it, like maybe a spoon, and put it on the outside of the kitchen stuff to remind me that it's kitchen stuff. In the same way, we can take the integers, and any integer that's divisible by 2 goes into its own box. And just so we remember what went in there, we put one of them, the 0, on the outside to remember what's in there. So 0 is the representative. Likewise, I could do the same thing with everything else, the 1 box. And so I'm going to take all the odd numbers and put them in another box, and I'm going to put a 1 on the outside just to remind me that the odd integers ended up in the other box. So 0 and 1. And what you can find out is that you can actually add the boxes. I removed the picture of the cubes because, first of all, I don't draw well, and second, it's easier to work with them when they're not in cubes. But I can add the 2 boxes to each other. So if I took the entire 0 box and added it to the 0 box, I would get another even set of evens. So 0 plus 0 ends up being 0. And 0 plus 1 ends up being 1, because if I took the evens and added it to odds, I would get odds. And likewise, 1 plus 0 gives me 1. And 1 plus 1, if I took the odd boxes and added them twice, I would get the evens. So that's the 0 box. And so I have a Cayley table. And so Z2, which is basically those 2 boxes, with plus defined as above in the Cayley table, forms a group. So I know everybody has seen this before in one form or the other. The definition I'm giving you now is called a partition. A partition is actually exactly what I described. It's a breaking up of the boxes of the original big set into little sets, into little disjoint sets that are self-contained. Z3 would be a packaging, or what we call a partition, of the integers mod 3. There's going to be 3 packages. There's first going to be the numbers that are divisible by 3. That's going to go into the 0 box. Then there's could be a possibility of having a remainder of 1. Those go into the 1 box. And then there's remainder 2 possibilities, and they go into the 3rd box. And you have a Cayley table with that too, and so on. I'm not going to develop the Cayley tables. Notice, for example, Z6 is also a group. They all have inverses, and I think undergraduate class, some of you haven't had it for a while, but you spend time actually picking out the inverses for a particular one of these, Z2, Z3, and Z4, so forth. So you can just check yourself, make the KLA table for Z6, and like we did last time with the Klein group, pick out the actual inverses for different elements, and that you'll see that it indeed is a group. But if I take the three elements 0, 2, and 4, those three elements form a subgroup of Z6. First, it's closed, because if I do any addition back and forth, it remains self-contained. So the subset H is closed under addition. E is 0. From the big group, the same E is the E in the small group. So E is in there. So I'm fine there too. And it contains its inverses. 2 plus 2, the inverse of 2 is 4, and the inverse of 4 is 2, and both are inside there. So I'm fine with that too. Notice I did this little calculation here too, that 4 plus 4 is 8, which mod 6 is 2. Just to remind you, I'm modding by 6. So I have do number 1 on in-class assignment. It must be to get myself to shut up and look at see what we have. Hope it's something interesting. Okay, there's a series of different kinds of sets here, the original group, and they are all under addition. And the question is whether these other things are going to be subgroups or not. So you can't work in groups today. I guess you can. You can message each other privately. But maybe you could take a stab a few minutes at trying to determine if they're groups, and then we could come back together and see what you get.